turn it on.
Wow. What a serious looking Martin. And
yeah, that's, oh, I think I need to.
You look very distinguished there.
Who looks distinguished?
You even.
I look distinguished. I look young. That was 7 years ago now.
Maybe.
Time flies by, yeah?
Maybe that's the one.
Yeah.
No, that's how we hired him.
Yeah.
And that's what we got.
Look what they did to me, yeah? Look what they did to me.
That's the problem. Probably the also, how is it in Germany? Can you get your haircut? Or?
Yeah. Now they opened.
I have a haircut now. I have a nice haircut. My wife complained that it was a little too short for her taste. But
you never know how long it has to last.
Yeah, that's true.
Well,
I think we're okay. You know. Let's see one quick thing. Let me see if somebody else is waiting from, because sometimes also. Oh, Burkhard is here. Sorry. Let me get Burkhard in.
Oh, I see 79, 81. Yeah, it's fun.
Let's see if Martin is
also. See at least how many people.
Yeah, you can, and then online it's about 21. But
yeah. Hello, Theo and Jairo. Why let you wait us for such a long time?
Hello, Burkhard.
We're sitting outside watching you.
You're sitting outside.
Yeah, Jairo didn't let us in, so.
Yeah. And I only let, only the troublemakers are not allowed to come in until the last minute, yeah.
You are in quarantine, of course.
Sorry, I was just blabbing about with, but I think Martin is the only one, but maybe Martin is not available today. But he'll come in a minute. I'll try to keep an eye. Very good. I keep official time with my, there we are. Okay, so let me begin. To thank everybody once again for attending the SPICE-SPIN+X seminar series online. Once again, this is organized by myself and Karen Societe in the Spin Phenomena Interdisciplinary Center in collaboration with the Collaborating Research Center of SPIN+X between Kaiserslautern and Mainz, led by Martin Schliemann, Burkhard Hillebrands, and Matthias Chloe. And it is a webinar, meaning that you only see the speaker on the slides that I share at the time, but you can ask questions in the Q&A part and write them there. And at the end of the talk, I will give you the floor to ask the questions directly. And if you cannot if your speaker doesn't work, I can ask a question for you. We have it every Wednesday at 3 p.m. And then, of course, we continue recruiting good speakers, keeping in mind the broad audience. And please give suggestions if you like. Today's person that needs very little introduction is Theo Rasing. He's very famous or infamous, depending on how you look at it. But a fabulous speaker, very entertaining all the time. He's from the Netherlands now in Radboud University now for a while, and he has a long list of, as you can see, of awards and achievements, and it's so long that I would take the whole seminar to say them, so I won't. I think his best achievement is he still looks younger than me, even though he's not. And with all this nice hair, and we were discussing, my hair looks white, his looks exactly the same, and that picture was taken a long time ago as well. So I don't know how he does it. I think it must be the photo there and there. But with that, I'll stop here sharing, and I'll ask you, Theo, to please go ahead and share your screen and start whenever you like. And the floor is yours.
Okay. Did it work, the sharing?
Yeah, perfect. It looks very good.
Perfect. Well, thank you for the introduction. I will make no comments about your or my hair, but it's a pleasure to be here, at least be here online with you. And what I would like to talk about today is indeed the control of magnetism with light, in particular with very short laser pulses. I like to sort of sketch the development from the very beginning towards the more practical issues and the latest development in sort of, well, first steps towards brain-inspired computing. Okay, so, well, this picture down on the left there, the
One thing, Theo, your microphone is a little bit.
Oh.
Which microphone are you using?
Just directly. I always use it just for my laptop.
Okay, that's okay, but you don't. I think you're touching on top of it, and
maybe I was shading.
your hand. Okay.
Right. Thank you. And oh, now it's frozen.
Okay.
Somehow. That's
maybe if you want to restart it, it's okay.
I guess I should maybe. I can't do that either.
It's okay. It's messing out.
I'll stop share for a second.
Yeah. No. Sometimes that's what happens. It's okay. So you're very active, moving around. That's why.
I guess that's right. Now let's go back to the. Oh no! Now I started too early with this. First, I have to go back to the webinar.
No problem.
Our screen.
I can always tell a joke in the meantime, I guess.
Okay,
there you go.
Your job then.
It's coming. Yeah.
All right. Okay.
Yeah, okay.
So let's move on now. Now this works. In Nijmegen, of course, we're not only playing with my femtosecond lasers and magnets, but we also have, I always need to introduce that, our, of course, high field magnet lab, which is coupled with the free electron laser PHYLX. So basically there we have a whole, let's say, set of free electron lasers covering let's say 1.5 micron up to the terahertz regime and millimeter waves. And that is directly coupled to the strongest DC magnetic fields that there are. So that's up to 40 Tesla. And the nice thing is we can also do the kind of work that I'm describing today, that is pump probe experiments in this kind of fields. Okay, now let's start with a little introduction, and that is data. Data is nowadays being called, well, the new oil. And that's not so strange if you look at the development of data and the whole data industry. And maybe if you just want to look at the economics of it, 10 years ago, the largest companies in the world were indeed oil companies like Shell and Exxon and BP, and now it's the Google and Facebooks. And that has to do with the fact that it's the enormous amount, the big data, and also this cloud computing. The present computers that we use are very powerful, but we use a lot of storage in the cloud. Now, if you look at that, then you see that this is indeed exponentially, it's really exploding. And this is not even counting what has been happening the last years with all this Zoom or Teams of whatever kind of format you're using. So this is clearly not very sustainable. And why is that? Because, well, lots of data also means lots of energy. As I already explained before when I was talking to Jairo, I was, of course, looking forward to come and to come to his house to enjoy his wine cellar afterwards, of course, after the talk. But, well, if you realize that in order to find this, we use Google these days, but you have to realize that if you do this 30 times, it takes as much energy as to bring 1 liter of water from room temperature to boiling. And that's just 30 Google searches. Only that searching, we do already like 6 billion times per day. And that's just this one type of application. And for that reason, these huge data centers like Google and Facebook is building everywhere, they already consume together 7% of the electricity produced worldwide. And that is because it's not just Google, it's Facebook, it's Twitter, it's you name it. Right now, this is also, as I understand it correctly, immediately streamed via YouTube. Now, if you think about data, then magnetic storage has been always the way to store data from the very beginning. If you're looking to the very first hard disk drive, this picture, of course, many of you probably do know, that is already from the 1950s. It has an astonishing capacity of 5 megabytes, and it costed $50,000. Now, of course, nowadays we have these conventional hard disk drives. There's a lot of development in the last decade, and particularly in the area of magnetic random access memory, or MRAM. And if you now look today, a 3 terabyte hard disk drive costs about $100. That means that's about 3 cents, $3 per gigabyte. If you convert that for the original hard disk drive, that would be $10 million per gigabyte. Talking about nanotechnology, by reducing the bits has not only becoming very small, but also extremely cheap. And that is still indeed why, let's say, the majority of all, especially the archival and all kind of storage, is always magnetic, because it's extremely cheap. There's nothing that can compete with that. Of course, in size, things can compete. Like if you look at this very small solid state drive, but indeed that is very convenient, but it is not really for the, let's say, mass storage that is needed. Now, I wanted to talk about all-optical switching. And let's first think about this. Usually, of course, an experimentalist doesn't do that, and this is also fortunate, because otherwise many things would not have been discovered. Because if you think about it, you know that, well, the best way to, let's say, rotate a spin is by applying a magnetic field, and you do that by applying a torque. So that means you apply it perpendicular. And so if a laser pulse would sort of work as an effective field, and you want to do that with a very short laser pulse, then for a 100 femtosecond laser pulse to reverse magnetization, you need almost 100 Tesla. So you need an extremely strong laser pulse, which is something that, well, this is about the strongest pulse that people can make, but then when people do that in magnetic field labs, like also in Japan, it's usually a one single shot indeed, because then not only the magnet is broken, but usually also your sample. And so if you don't have such strong pulses, then basically you need to keep it on much longer. So it doesn't look very promising to really use a femtosecond laser pulse as a way to switch the magnetization. Now let's think about the interaction of light and magnetism. And we all know that, of course, because then we look in magneto-optics. And so if you're looking at the, let's say, dielectric tensor, in the case that you have a magnetic or a magnetized medium, and suppose the magnetization direction is, in this case, in the z direction, then typically you get off-diagonal elements, like in the x, y, y, x direction. And these elements, for instance, give rise to very well-known parameters like the Faraday effect or the Kerr effect or other kind of magneto-optical effects. However, already in the 60s, people realized, at first theoretically, and later on also experimentally very quickly after that, that of course, if magnetic medium can interact with light, then light should also interact with the magnetic medium. And so next to the Faraday effect, there should exist something like the inverse Faraday effect. And this was indeed, Pitievsky sort of predicted that, and Van der Ziel et al. Also indeed demonstrated that. But this was already a long time ago, and then it was basically forgotten. And the reason is that, well, with the lasers in those days, the effective magnetic fields that could be generated were very weak. However, some, let's say, 2 decades ago, we sort of reinvented this, and we used the inverse Faraday effect to do a sort of all-optical spin resonance. What do I mean with that? We took a crystal, which was an orthoferrite, where the spins were antiferromagnetically ordered, but they're not totally antiferromagnetically ordered. That means there's a small tilt, So actually not in the direction of the spins, but perpendicular to that, there is a small magnetic moment. And so they have a magnetization. And that means you can also use the normal Faraday effect to probe that. So the experiment now was that we excited this with a circular polarized laser pulse, and then we probed what was happening afterwards with a time delayed linearly polarized pulse and looked at the dynamics. And the results are displayed here. And this shows that indeed using a laser pulse, we can excite these spins and excite ferromagnetic resonance in this system. And it is probed by indeed a optical pulse. So that means it is only optics. There is no magnetic field or other than purely light that is being used to excite and probe these resonances. But what you also see is that if you change the helicity of the excitation light from light-handed, from left to right, I see there is a small mistake. I only see it now. I used this slide many times, but now I see it's both times it says left, but it's right and left. Then you see that basically, indeed, of course, you excite exactly the same resonance, but because the field, the effective field is now in the opposite direction, the phase of the resonance is exactly opposite. And further, you can look at, and you can analyze the amplitude, and then you find out that such a 100 femtosecond laser pulse, in this case, has roughly the strength in the order of a Tesla. And but indeed, it only moves the spins. The spin is really only tilted by a few degrees maximum. Now you can look at the intensity dependence here, and you can use that. And then we find that we can actually induce even much more, let's say much stronger laser pulses, so effective field pulses, up to the sort of damage thresholds. We can make tens of Teslas, but still that's not big enough to really do reversal. So how can we switch? Well, we managed to do that a couple of years later, but in a totally different system. In a system that is gadolinium iron cobalt. And here you see the results of this. I will not give a lengthy introduction because I think many of you have seen this. But I just want to point out here that you see here two large domains. On the one on the left-hand side, white domain magnetization is up. And there you see that if you come with a certain helicity, nothing happens. But then if you go to the dark domain where the magnetization is down, you reverse the magnetization with a single 100 femtosecond laser pulse. And so you see that one single pulse is enough to reverse the magnetization. And if you take the opposite helicity in this case, then you see that you write domains in the white domain, but not in the black. So this was a very exciting result those days. And then the question was, what is actually happening here? As I just showed you, or try to sort of say that if you estimate it theoretically, then this was unlikely to happen with a 100 femtosecond laser pulse. And indeed, if once we started to analyze this, we realized that it is a little bit more complex than a simple effective magnetic field. And what is important in this case to understand this switching mechanism is to realize that this is not a ferromagnet, also not an antiferromagnet, but a ferrite magnet. And that means we have two sublattices here, it's iron and gadolinium, and they're very different. They are antiferromagnetically coupled, which is important, but also they are quite different in size. The magnetic moment, especially the atomic magnetic moment of gadolinium, is about 4 times as large as of iron. So there is a big difference, and it appears that because of that, although they are very strongly coupled, if you excite such a system on a very short time scale, you sort of decouple it, you bring the system in a very strongly non-equilibrium, and as a result, as a result of that, you find that on the very short time scale, on the sub-picosecond time scale, the dynamics of these two sublattices is very different. You see that iron responds on almost instantaneously on 100 femtosecond or so time scale, whereas gadolinium is about 4 times slower, which is indeed sort of what you can expect if you think about the ratios between the magnetic moment. And if you consider that, and you consider the angular momentum exchange between the two sublattices, then you can understand the mechanism of this switching. And interestingly, then you find that both, let's say, theoretically and also experimentally, that this antiferromagnetic ordering for the time between, let's say, about a few hundred femtoseconds to 1.5 picoseconds, you see that both the moments point in the same direction. So this switching goes through a kind of a transient ferromagnetic phase until it recovers in the other opposite stable antiferromagnetically aligned state. So this is basically how we understand this now. And so it means that this switching is not really driven by an effective magnetic field, but it is really driven by the exchange. And if you think about it, the exchange interaction itself gives rise to a very strong effective field internally. Now, that's all nice, of course, but then if you want to think about applications, you want to go away from the micron scale towards more, let's say, real bit sizes of nanometers. And we managed to do actually by indeed using a development that was done in optics, and that means using a plasmonic antenna, which is able to excite a system. When you excite an antenna, when such an antenna is simply a kind of a dipole antenna made of very thin, small gold flakes. If you excite such an antenna with an optical laser pulse, then light is being focused, and it can be focused down to in the tens of nanometers. And what you see here now is on the left, you see just the initial film. So we had such a gallium ion cobalt film with a lot of these antennas. We zoom in on one, then we excite this, and you see with one single shot, you find that indeed the magnetization is reversed. Blue becomes red, and the next shot indeed reverses this back, and then you can go back and forth, and this is very repetitive and very stable. You also see that this is a real experiment and not a simulation, because, well, when we simulated it, we would expect that actually the switching would happen exactly in the middle of this dipole antenna, because that is where the concentration of light is the maximum. But here it happened on the other side of the antenna, which had to do with the inhomogeneities of the sample. But as a result, we can switch now at the 40 nanometer length scale, and indeed on the picosecond time scale. So now, if you sort of summarize this, if you look how this development is of magnetic storage, starting with indeed the first hard disk drive to the present day hard disk drive typically takes about a nanosecond to switch a magnetic bit, and it takes about 0.1 nanojoules, or about 100 picojoules to switch. If you think about that, that is actually an enormous amount of energy, because of the fact that if you really look what is the energy barrier between the two stable states, that's in the order of, well, for a stable magnetic bit, we talk about 60 kT, which converts to about 10⁻⁹ joule. So there is a world to be gained there. Now let's see what we have accomplished. If we do this optical switching with a femtosecond laser pulse, and we can do it now on the nanometer length scale, then this converts to about 10 femtojoules per bit. It's not close to the absolute minimum of 10⁻⁹, but it is already orders of magnitude better than what is being done in a hard disk drive. Now, of course, this 10 femtojoules is the energy needed to switch this very small bit. But in reality, of course, you throw away all the other light because this is only that part which is focused through this antenna. So in order to actually do this, we really have to bring the light in a more efficient way down to the magnetic bits. And for that, we had our interesting and very nice SPICE project, the Spintronic Photonic Integrated Circuit Platform for Novel Electronics, or SPICE. And indeed, it was very interesting when I was writing this proposal more than 5 years ago. I discovered one day before I had to submit it to Brussels that SPICE was already taken. But fortunately, we came to a good agreement with Jairo that I could still use this acronym. I had absolutely no idea at that moment. Anyhow, the idea of our SPICE project is that we combine now a magnetic random access chip with a photonic chip, and in this way couple the light from one laser through a photonic network directly to the different bits. Basically, the plan was to make a demonstrator of 8 bits, and we had hoped to achieve at least 10 to 100 times more energy efficiency. And we actually came very close. Basically, we just filed our final report. And indeed, we got basically the thing almost completely to work. And so these are a few very recent results of this project. But it's also clear that we haven't really, well, it's not being mass produced yet. There are still some practical hurdles to be taken, but the proof of principle is actually there. Okay, now that we start talking about practical applications, let's look at the practical applications of more standard hard disk materials, not these rare earth transition metals, although they are very nice for all these demonstrations. But people always ask me, why not cobalt platinum or iron platinum? Well, it was already demonstrated some years ago, including, well, I don't know if Martin is here, but at least work from Eschliman, that actually you can use optical femtosecond laser pulses to reverse the magnetization. This was reported in this paper, and here you see that when you move a laser beam over such magnetic domains, then you can reverse it depending on the helicity of light. What I have to tell you here is that, of course, this is the results of many, many, many laser pulses. So the question is actually, what was the mechanism? Well, we looked at this, and so we also studied some of these materials, such a cobalt platinum multilayer. And then we first started to do some systematics, changing the lengths of the laser pulses and finding out that actually, if you really use very short pulses, what we normally did, 100 femtoseconds, then basically you end up in a multi-domain state. But if you make the pulse width a bit longer, then you ending up indeed in a nice and reverse, homogeneously reversed. So it's clear that pulse duration is important. Another parameter you can change is, of course, the fluence. We did the same. And here you see, and that is also what we knew already with our all-optical switching, the switching process itself is sort of a threshold process. If the fluence too low, nothing happens. Then you reach a certain fluence, it switches. And then if you keep increasing the fluence, you basically, the switching probability goes down, and basically it goes back down to 0. So basically you demagnetize, which is basically you're putting too much heat in your system. All right, so we can make a whole phase diagram of fluence and pulse durations, and but that doesn't really tell you yet what is the mechanism. So for that, we zoomed in a little bit, and what we did here is if you excite such a system first with one laser pulse, and then you start looking under a microscope and you find a place where you have a domain wall. Now you put your laser exactly on the domain wall, and then you start observing what is happening after a number of pulses, whether you use right-handed or left-handed circular polarized light. With this, of course, we used here very low fluence so that we could study this very, let's say, carefully. And then you find that basically what happens is that you move these domain walls depending on the helicity, either in one direction or in the other direction. So if you take this together, all these experiments, and basically what happens in this type of reversal of this cobalt platinum or iron platinum is basically very similar. It is basically a sort of nucleation.
Make sure you don't touch the microphone.
Sorry, I was being, let's say, the two-step.
You're very excited.
And I'm getting. Thanks for warning me. So it's this two-step process where, on the one hand, you get nucleation of very tiny reverse domains, and then it is a growth of the one domain direction with respect to the other, and that depends on the helicity. Now, this is of course nice, but well, hundreds of pulses is not very nice. Here, if you look at a certain fluence, it only moves a few nanometers per pulse, so that's why people use hundreds of pulses to do the reversal. And the question was, of course, can't we do better? Now, I had a very smart postdoc, and then he thought, well, if it's such a two-step process, then maybe we should sort of disentangle these two steps. And so let's take a sort of dual pulse approach, where we take two different pulses. The one pulse we use for nucleation, and the other pulse we use for deterministic growth of one domain versus the other. And so we start with a very short, intense, but normally linearly or unpolarized, it doesn't really matter, femtosecond laser pulse. And then after a specific delay, we come with a somewhat longer circular polarized light. Okay, so this then, we take cobalt platinum. Again, this is the sample, this is nice perpendicular loop. And now here you see the results, where we use indeed two pulses. You see that in this case, the separation between the pulses is 2 picoseconds. The first one is 60 femtoseconds, is linearly polarized, and the second one is 3 picoseconds. So, and then you see that after about 4 or 5 pulses, basically you have a complete reversal. And if you take the opposite helicity, then you go from dark to white, but the number of pulses is the same. So 4 pairs of pulses can fully switch magnetization. And that means instead of 100, 4 pairs is still 4 times 2, but it's only 8. So it's more than an order of magnitude we have already gained. Now we can zoom in a little bit into the pulse separation, because what I showed is just typically only one separation that was 2 picoseconds. If you do this more in detail and you follow it, then you find that there is a very sharp, basically optimum, where you completely and fully switch when you have a pulse separation between the femtosecond and picosecond pulse of about 5 picoseconds. And if you much longer, or then there's hardly any reversal if the direction is even negative. So that means first is the picosecond pulse, and then is the femtosecond pulse. You basically get only demagnetization and nothing happens. So this comes very close, and we have been optimizing this, and basically we're just preparing, or basically we have submitted these results now. That 1 pair is basically enough. So you have only 2 pulses. And that means that there's an enormous gain especially in time, because if you have these hundreds of pulses, then you have to look at the repetition frequency of these lasers. And that means in this one pair, you basically are done in 5 picoseconds instead of milliseconds otherwise. Okay, now, so that basically summarizes this part. And that means that indeed we can optically switch ferri and ferromagnetic materials. We can actually excite antiferromagnetic materials, but switching there is a little bit more of a challenge, although there are ideas about that, but I will not talk about that. But in Nijmegen, Alexei Kimel is particularly very keen on trying to achieve that. Let me, at the end, switch gears a little bit and not only talking about magnetic storage, but about the, let's say, computer processing more in general. Well, end of Moore's law has been predicted already many times in the past 6 decades. But in the last years, it's been done by even Intel itself. And why is that actually? Well, it's not because ASML in the Netherlands cannot make these bits or these transistors smaller and smaller. They can. The problem is they're so small that with all the currents that goes through it, with nowadays you have, let's say, 5 billion transistors on a chip, you generate way too much heat. If you take off the cooling of one of these chips, you see it go up in smoke in front of your eyes. And the other part is that in present-day computing, you have a processor and you have a memory. And data is being shipped back and forth all the time between the processor and the memory. And that also means that there's a lot of joule heating that goes with that. So this is what they call the so-called von Neumann bottleneck. And the question is, can we not do better? Especially considering this enormous explosion of the amount of data and information that we are all generating. How can we do this? Now, people start looking at the brain. And well, people have been start looking at the brain maybe earlier, but now I want to look at it in a certain specific way, and that is about the capacity of our brain and about the energy consumption. Well, the energy consumption is clear, and fortunately, we only use it in the order of 10 watts and not the megawatts that the supercomputer uses. Otherwise, we wouldn't be sitting here or standing here. Well, what is the key of the energy efficiency of the brain? I have to be careful because I'm definitely not a neuroscientist, but there's one thing that I have learned in the last few years, and that is the processing and storing of information in the brain is massively parallel and it's integrated. You have no separation between a processor and a memory. It's all integrated. And whereas in the computer we know it is separated and also everything is serial. That's why we're very happy with a, let's say, clock speed of several gigahertz, because all these steps in the computer go one after the other. And fortunately, with this, well, typically biochemistry, which is going on in the brain, maybe steps take milliseconds, but because millions of steps go parallel, it is still efficient. And yeah, a very strong, let's say, breakthrough was actually of let's say, this neural networks was a couple of years ago, when this Google AlphaGo could beat the world's champion in Go. And how was that possible? Let's say 20 years earlier, the IBM Deep Blue, the supercomputer at that time, could beat, for the first time, the world champion in chess. And their approach there was basically feeding the computer with the rules, and then it was basically brute force, meaning that every time the computer would go through, but very fast, of course, through all the potential steps and then choose the best one. However, even with today's supercomputer, this would never work for Go, because there are simply too many different possible moves that this is impossible. This is something like 10 to the order 170 or so. So this doesn't work with a brute force approach. However, this program, AlphaGo, could do this because it had two things that it has in common with our brain. And that is, it could learn and it could do pattern recognition. And so it also started with having the rules, but then the programmers let the computer play against itself. And because a computer doesn't get tired and can play 24/7, at the end, indeed, it was capable of indeed beating the champion. And so this showed that indeed we can do these neural networks that are inspired by the brain, and they can learn and they can do something else, and that is this pattern recognition. But now it's a program that learns, because it still used the supercomputer to do all this work. And so this is, of course, impressive. And well, artificial intelligence and neural networks are being used more and more because, well, this helps us indeed solving very, let's say, problems with large databases, but it's certainly not energy efficient. So if we want to do something energy efficient, we have to make different hardware. The hardware has to learn, not the software. And that means you need materials that can learn. Now, for that, you actually do have to sort of understand a little bit how a neuron works. And well, we know that these neurons are being connected, and each neuron, we have about 10 to the 13th or so neurons, and each of them are connected with thousands and thousands of synapses with others. So you have single neurons connected by lots and lots of synapses. And these synapses, they can adapt. Somehow the learning has to do with the changes of the connections. And so this is then what you can also try to do. Well, this is basically the scheme. And this is also how you can do this in the software. You have inputs, you have certain weights. These are the strengths of these synapses. And then at some point, if these weights are going together past a certain threshold, then a neuron will fire. And so now this is what basically people try to do in neural networks in this. And now we try to do this now in materials. And people have started already in our own community on, and let's say in spintronics. Julie Grolier is very strong in this field and has been demonstrating that you can use spin-torque oscillators for that. Some other people use other materials like, let's see here, some gold nanoparticles or ferroelectric instead of ferromagnetic materials. And on the other hand, the learning here is not really done in the materials. The learning is still done in an external computer. So these, let's say, the weights of the synapses is basically stored in a computer. And so what we try to do is, can we really not use materials that can learn? And so now, of course, I want to use magneto-optical materials because I know I can change the magnetic properties with light. And so now we started with a very simple type of perceptron with two inputs and an output. And then we have a feedback system. And so if the output is not good enough, then we go back and then we change the weights and then we adapt them. And now, so this was the idea. Now we want to do this in a material. That means we now use a magneto-optical material, and let's say the synapses are, let's say, within the material itself. It has to do with the magnetization, is basically the weight. And of course, now we're going to use this nice cobalt platinum with single pulses, because there we need many pulses to change. And so now we have something that is not a 0 or 1, but can continuously change between these two values. And this is exactly what you like to do if you want something that sort of acts like a synapse. Now, this was supposed to, no, it doesn't. Okay, sorry, that was basically a small movie, but I'm glad that everything else works. So here you see basically what happens if you keep pulsing with either right-handed or left-handed. So you can go from, there are a number of shots and you see numbers of pulses there. So from the left to the right, if you see with the right-handed, you start with a completely black and then you change it into completely white. And then you start reversing and so you can go back. And the results are also plotted on the right side. So you see that you can continuously nicely control the weight. So this is kind of a, let's say indeed, magneto-optical synapse now, controlled by optical pulses. Now we want to use this to do some very simple pattern recognition. Now we started indeed simple by just a 3x3 matrix. And then you can only write very simple letters, like this is my Z. So it's a very simple Z, but okay. You get the message. And then, of course, the idea is then not only that once you can, let's say, learn such a network that this is a Z, it should also recognize when somebody is like writing in a slightly different way. And that means you start flipping some of these pixels so that it is basically a very noisy Z. And then the idea is, well, once a network has trained that the picture on the left is a Z, then it can also hopefully recognize the others. So we did that for 3 different letters, for a Z, a V, and an N. And then we basically, you need training. And then here you see how that works. On the left, you see first actually a theoretical, and then on the right, the experimental one. And basically after about 400 steps, this learning is completed. And so we did that for, let's say, 8 out of 10 every time. And then the 2 others were, that was then the challenge. So learning was done on 8 patterns, and then the 2 others were every time were 100% classified. So in principle, proof of principle, it does work. So then if you look at the final results, then of course we use very large synapses now with, let's say, 65 picojoules per synapse per step. But if we can scale this down, then we come in the same sort of energy regime as we showed before. We're coming down to tens of femtojoules per step. So this is quite promising. And of course, we need more inputs so that we can have a real letters or other things to be classified. And then, of course, we have to test this against the standard in this database. The other thing is we want to also use and go into other more 3-dimensional structures. And of course, we have a special ways of doing this together with our colleagues here in Mainz, Matthias, but also with Dunin, Pukowski, and Blugel in Jülich. But that is for a next talk, hopefully. So in summary, I'll come to the end to leave some time for questions. What I have hoped to show is actually that, although maybe at the beginning counterintuitively, optics and magnetism go very well together. We have managed to indeed write magnetic bits on a picosecond timescale roughly, and with an energy of about tens of femtojoules. From that, we are approaching real applications, although it's still challenging. I'm very honest about that. But on the other hand, the way things are going right now with this enormous development of energy consumption in the IC, it is also important to develop other approaches. We have made some first steps in that direction. And one of the things I hope to do is actually combining these 2 things, because once we can indeed use such a photonic network, we can indeed start really parallel processing in our magnetic sort of magnetic brain, let's put it that way. And so at the end, we hope that we can indeed achieve that and achieve learning on a chip with light, of course, or with the speed of light. And with this, I come to the end. Not before I want to thank a lot of people that were involved. And I mentioned this Ashim Chakravarti in particularly because he was involved in this last part of this neural networks. And I thank all of you for your attention.
Okay, thank you very much. So let's see, I think Sasha has the first question. Let me give her sorry about that. Hi Sasha, good to see you. Can you ask your question? Do you have your speaker on?
Oh, yes. Can you hear me?
Yeah. Hi, Sasha. Hello.
Yes. Hello, Theo. Yeah, thank you very much for a very interesting talk. Well, my question is about this switching with two pulses, with the linear and then circular polarized. Mm-hmm. Do I understand correctly? So the question is that does this experiment prove that it is inverse Faraday effect works there, or it still can be explained by means of magnetic circular dichories?
That's a very nice point. Basically, if you look into the details, what you do is the following. First, indeed, you create, let's say, nuclei, and then you can explain it. It's most likely by magnetic circular dichroism and not the inverse Faraday effect.
Oh, okay.
It has to do with if you're really looking at the time dependence of all. We have also I didn't have time for that, but we did do pump-probe experiments in this process. And basically, so it is mostly the magnetic circular dichroism that creates, let's say, a gradient over a domain wall and pushes it in one direction or the other. This is the current understanding.
Okay, thank you.
You're welcome.
Excellent. So the next question is from Igor. Igor, go ahead and ask your.
Hi. Thank you very much for this enlightening talk. It's like touching the future right now. And I apologize in advance for my question, but I had to step away for about 5 minutes in the middle of your talk. So maybe you have actually said that, but then I'm sorry about. But the question is that about 40 years ago, there was fashionable activity of teaching training spin glasses, Hopfield spin glasses, in terms of adjusting the random exchanges so that to have local minima in prescribed image minima, and then recovering them by heating and cooling that back. Is it related to what you are talking about?
It's in a way, it's a little bit related, although I didn't really talk about that specifically.
Okay, I'm sorry.
But to be honest, a colleague of mine here in Nijmegen, Alex Kachatorians, is exactly following that direction. He is trying to do this, and he is really doing that, making a sort of artificial spin glass, but he using, let's say, pump probe technique. So we can really look at the individual spins of individual atoms, putting them randomly, changing their interactions, and using indeed temperature to tune that. And so this is very much related, and his motivation is exactly the same, trying to see if you can achieve a network that can learn. And he's actually demonstrated that. He has just recently a Nature paper out, just a couple of weeks ago.
So maybe I can continue a little bit.
No.
No, it's very interesting, in fact, because at that time there was an off-spin which was sort of abandoned because I guess people just didn't have enough power to investigate it. That's about making your spin glasses to dream. So essentially, it turned out that you can improve their memory, but by letting them randomly remember everything that had been ever stored in their memory and sort of sharpen the Hamiltonian to adjust it. So it's literally letting this network to dream, and then it remembers better what it should remember. Anything along this line?
I think this indeed takes more time. We should. I would be very happy to discuss this further with you.
Okay, all right, sorry about that. Okay.
But no, it's very interesting. And you see things come back, like the inverse Faraday effect. was
that's right. That's
in
right.
the
Yeah.
60s and then forgotten until
40 years later, things come back. Yes.
That's usually the fact. A lot of things are just sort of reinventing of wheels, but more fancy wheels.
Yeah. So let's go to the next question on the GOTS, which is actually related to the inverse Faraday effect. Go ahead and
So thanks for the talk and thanks for the opportunity to ask. My question is simple. What do you know about the microscopic mechanism of the inverse Faraday effect? What is really required? Is it necessary to have spin orbit coupling, or is it just about circular currents which you excite? What do you know?
So it's basically, if you're looking at the microscopic mechanism of the inverse Faraday effect, at least especially in the systems that are very well sort of understood, and these are in these dielectric materials that I demonstrated in this orthoferrites and others. It's basically kind of coherent Raman scattering. So what you do is, I don't know if you can see my hands.
Yes, I do.
Yeah.
Mm-hmm.
Okay, because what you do normally is you want to bring a system from one level to another level, but these levels are very close together. With an optical pulse, you're coming with an energy which is way larger. But what you do is, because you have a large, like you have a short pulse, let's say 100 femtoseconds, which has a certain pulse width. So the going up and then pumping down is, these two are coherently they are in the same pulse. And so in this way, you can very efficiently bring the system from this level to the other level and switch. And so this is how you can sort of in a microscopic way understand this inverse Faraday effect in these dielectric materials.
Okay.
Very good. So Georg, go ahead. You have a question?
Yeah. Hi, Theo. Good to see you again, although you cannot see me.
No, I can't see you.
It's very nice to see the progress that's been happening over time. I have a question concerning the neural network or the programming that you're doing. I mean, if I understand correctly, you're programming the weight functions by the light.
Yeah.
And my question is, do you also use these program parts for the recognition, or are they just storing the weight function that is used somewhere else? So is there some light projection onto these pixels that helps with the recognition, or do you just use the weight function from the pixels to do the recognition somewhere else?
No. You do it. You really, let's say, you change the weights in the material, and then you come with indeed light through another pattern through this let's say film, and then so you basically use that in the film itself. So you go through it, and then you have the weights. You're probing those weights, and this way you can do your recognition.
So by the Faraday effect, or
yeah. You do use magneto-optics, of course.
Okay, thanks.
Great. Massimo, go ahead and ask your question.
Yeah. Hello, Theo. Very nice talk.
Thank you.
I would like to ask you something about, in the beginning of your talk, you described in some detail how, the time advantage and the energy advantage in doing this optical switching, which is similar to basically writing or erasing a bit in a certain sense.
Yeah.
What about reading? Because that is also important for the efficiency of the overall system. You have to read your memory.
Yeah.
Do you have a similar gain in energy and time?
Well, in reading, of course, see, the thing is, in the, let's say, the sort of chip that is still on the slide there, which we sort of demonstrated proof of principle, there we write optically and we read electronically. The thing is, in the writing, the most energy is used. Of course, you can also read optically, but then the challenge is, of course, again, the same way that we need to bring this down to this small length scale, which with this photonic network, the magneto-optical effects can also be used to read it, but the most gain you make in the writing. So in this case, we write optically and we read electronically. But it is possible, but there is not so much gain to be had if you do this also optically.
Okay. Gisela, go ahead and ask your question, please.
Yeah, so thanks for this excellent talk. I have a question concerning the brain-inspired computing. There are a lot of other techniques to come to this neuromorphic computing. And if you read the very recent overviews of the solutions or the attempts, then unfortunately, magnetic materials play a very minor role. Can you comment on this? Or what is the real competition? Or are magnetic materials competitive in any way?
I can make an ultra fast answer. Come back in 2 years.
Everyone says this.
Yeah. No, but it is really true that indeed. No, I've been. I know about these developments. We have only started quite recently, and but I'm discussing this also with colleagues from IBM who know work much longer on this and know more about this. But I think the potential of using photons that are very energy efficient and using magnetism, which we also know that is very efficient in the way you can, let's say, store information in it and retrieve it because of the fact that it is non-versatile. So I think non-volatile. Sorry. So I think the potential is there, but I'm also aware of the fact that other people who have been working on this already for much longer than I have a certain, let's say, advantage at the moment. But I'm quite optimistic. Maybe a bit more than 2 years, but still. I hope to convince you soon.
Okay, thank you.
Yeah.
Yeah, I mean, I would like to comment on that a little bit because we also work a little bit on the antiferromagnetic spintronics sense with those things. So I think what is clear here that the other ones that have advantage so far at the moment is just because we've been working longer on the devices, on the synapses, on the neuron type of devices, but still are very slow themselves. Mm-hmm. So combining the speed, the efficiency, and the non-volatility will come most likely in magnetic and most likely antiferromagnetic materials, which can combine with the optical. And the ultimate need at the moment, I would say. So sorry, let's continue with.
No, but I totally agree with that. Of course,
this is
the antiferromagnet.
Exactly. Sangeeta, go ahead.
Ferrite magnets are almost antiferromagnets. You can tune them. Oh, sorry.
Hi, can you hear me?
Yeah, I do.
Hi, Theo. This is Sangeeta.
Yes,
hey.
Yes, I can also see you. There's a picture of you. It's not live, I think.
Thank you very much for such a nice talk. I have a question similar to Sasha. I think, what is exactly the microscopic mechanism for this two-pulse switching? So does the domain wall act as a seed? What actually happens in this switch?
Yeah, so this seed, with a linear pulse, we create seeds indeed. And then the circular pulse expands the seed. And it does that by indeed, well, we have been investigating whether this was the inverse Faraday effect or magnetic circular dichroism, and looking at the dynamics of this, it's the last one. So it's this.
If you started to pump with the X-ray, which resonates, for example, with the core states, then this would enhance. Is that true? Because if you are trying to enhance IFE or MCD, it should then give a enhanced effect. Is that possible to do?
That could be possible to do, but my sort of motivation here was to become very energy efficient with just 2 optical pulses. If I'm not going to the X-rays, I can probably do it, and it would be interesting to do, but certainly not. It would defeat the purpose of energy efficiency. I'm sorry.
Yes, that's true. Yes,
but
thanks.
It would be an interesting idea to probe that. Actually. Yeah.
Yeah. Thanks.
Okay, Jakub, go ahead and ask your question.
So thank you for a great talk. So I would like to ask about ultimate limit of the speed of the switching of the spin system in ferromagnets and antiferromagnets, because now it's hot topic, this antiferromagnets and antiferromagnetic spintronics, in which you can switch in a potentially in terahertz regime. This means the spin system can switch in a picosecond time scale. But you also mentioned that in for example, this gallium ferrite, that you could switch also in picosecond time scale. So what is the condition for a speed of the switching? And is it that there must be two sublattices? So there must be some resonance in terahertz, or like high frequency resonance?
Okay, well, first of all, to start with the last part of your, let's say, question, it's certainly not a resonance effect. So it is especially not if you look at these ferrimagnetic materials. There it is really to bringing the system out of equilibrium. You have two sublattices that antiferromagnetically coupled. You are, I mean, actually recently there has been, I forgot the reference actually, I had one or two extra slides. But anyhow, recently people have looked more to a complete phase diagram. And so what are the limits of pulse widths and energies, etc. And so you can play with that and optimize that. But basically, you bring such a system out of equilibrium and there's transfer of angular momentum between the sublattices. And depending on the details of your system, you always end up in the order of picoseconds. Now, in an antiferromagnetic system, there you have to find different ways, but then usually you have states that are, let's say, antiparallel in one way, and then you can maybe switch to 90 degrees. You have to look at you have to also then change, for instance, temporarily the anisotropy and do it in that way. And basically then again, the time scale is basically determined by the antiferromagnetic exchange, and for the same reason that it is in these ferrimagnets, brings you in the terahertz or in the picosecond time scale. So roughly speaking, that is always what you end up with. In the order, whether you have ferrimagnets or antiferromagnets, you are roughly in the picosecond time scales. To be honest, what will be the real challenge if you then start to really want to take advantage of that with really terahertz, let's say, data rates, then you need also to sort of get rid of your energy afterwards within a picosecond. That is quite an engineering challenge, which is not to be belittled.
Thank you. Also, Jeff, go ahead and ask a question.
Hi.
Hey, good to see you.
Good morning from California.
Yeah, good morning.
Thank you for waking up so early.
Well, as you said in the introduction, it's always worthwhile to listen to Theo. He's a terrific speaker. Thank you for the entertaining and very clear talk. I wanted to follow up on the question you were asked about your photonic or magneto-optical neural network. And you answered that you could also do the recognition using this scheme. And I'd like to ask you to explain a little bit more. When you switch these magnetic thin films, if you're reading them out by, let's say, Faraday or Kerr effect, we know that in these thin films, you know, the rotation is microradians. And so how do you get the readout signal large enough to actually do that readout function that you showed you could do?
Well, in these materials, I don't remember now exactly the size of the signals, but in this cobalt platinum layers, we could read them out using the magneto-optical Kerr microscope, and that was not too difficult.
Okay, thanks.
Yeah, no.
Right.
Actually, about you getting up, you got up at 6. I got also at 6 in the morning.
But he didn't have to.
That's 9 hours. I know that.
Well, just a little bit earlier to at least make a cup of coffee.
Okay. Well, I see why you don't have your camera on. I understand.
This is why this SPICE network, entices everybody to get up and stay late. No, that's very good. Sumit, go ahead and ask your question.
Yep. Thank you. Thank you for the nice talk. So my question is about this optical control of magnetization. When you want to control magnetization with the laser, we want the system to behave according to the laser parameter, like the polarization or time span. But at the same time, we are going to heat up the system locally.
Yeah.
So will this heating effect be beneficial or harmful, or it would have an importance to the whole process at all?
Well, this is also, thank you for the question. This was what I was alluding to already before. And that is, first of all, for this all-optical switching in these ferromagnetic materials, the heating is essential. You heat in a short period of time, like in the order of sub-picoseconds, because you have to bring the system out of equilibrium, and then together with the, let's say, the different dynamics between the two sublattices and the antiferromagnetic exchange between them, it will switch. However, if you want to repeat this, you want to get rid of the heat now as fast as possible. And so that means you really have to start thinking about engineering your whole system in a clever way, so that your repetition, your rep rate can be higher. And that is something that we haven't really focused on, but I do know that this is an essential issue if you really want to do this in a real device. And I think Jeff, who is much more practical and is a real engineer, at least he is an engineering department, so he knows better how to address that than I can, actually.
Just a quick question. In that case,
yeah.
Oh, sorry, can you hear me? Sorry.
Yeah,
go ahead and repeat your question. You muted for a second. Go ahead.
In that case, will the exchange gap play any role? I mean, if I have a large gap compared to this temperature, would it be an important case here?
I have to think about that. I don't think so. It really depends mostly on the actual amount of energy you dump in the system and how fast can you get rid of that.
Okay. Okay, thank you.
Yeah, welcome.
So I believe that's the last of the questions. So I want to thank you again. I will stop here now the streaming. So now the people we had 250